All right, so today in our last objective for this unit, we're going to focus on half-life calculations. And you may remember half-life a little bit from earth science. We're going to just review the definition, what you need to know about it, and then really focus most of our time talking and working with some calculations. So first off, the half-life is the time required for a material to decay to half its original or initial amount. So this is going to be, we have a radioactive sample. Okay, 100% of it is radioactive in that unstable nucleus. And then the half-life time is that time it's going to take for half of it to decay to a more stable form. So this would represent one half-life where we start off with 100% of it being the radioactive isotope. After one half-life period of time, half of it has now decayed to something else or something more stable, and that half of it still remains. So radioactive substances decay at a constant rate. So their half-life is constant. It is not changed or impacted by temperature, pressure, concentration, anything in the environment, which is why we can use it to radioactively date different materials. One little thing with this is that it's impossible to predict when a specific nucleus is going to decay and go through and emit a particle and undergo transmutation because it's a completely random process. But what we do know is that we can determine the amount over a certain period of time that will decay. We just don't know which ones will be the ones that undergo the decay. Another little piece is the shorter the half-life, the less stable it is initially because it's going to go through and decay at a very rapid rate. A longer half-life, like something like our uranium-238, is considered to be much more stable because it's going to take a long time for it to undergo and emit radiation and go through the decay process. So table N is really what we're going to be using a lot of today, where we're going to be using it to get our half-life amounts. And again, you can see these are, in our table because these samples aren't going to get changed or impacted by any outside factors. There are different ways that you can solve this. I'm going to show you one way that I find works well with students, and I'll be able to happily show you different ways in class as well. But what you have to be able to do is we're going to be determining how much remains after a certain period of time, the initial amount that might have been there after a specific period of time, the total amount that has passed from start to end, the length of a half-life when it's not listed in the reference table. So those are like the four main parts. I'm going to be using a diagram method for you, and you'll kind of see this idea where I'll be writing the amounts on the lines, and then my arrows represent the half-life times. So like in this diagram, I would be able to say that I had 3 half-lives, which would then give me information. Okay, so let's get into the examples so you can see how these go. And again, you want to have table N close by. So in example 1, it says how long will it take for 20-gram sample of a half-life of 2 hours to decay to 0.625 grams? Now in this one, it's telling us the half-life is 2 hours, so we actually don't need table N for this one. So I'm looking for my total time. I know my starting amount, and I know my ending amount. So 20 grams to start with, and then 0.625, this is my ending amount. And I want to know the total length of time. So I always put on my lines the mass. So I have my 20 grams. Okay, I want to decay that until it goes to 0.625. So I'm going to put, since I know the ending amount, I'm going to put my 625. Okay, and again, I'm always putting masses on the lines here, with one exception where we'll use fractions at a certain point. So I know that one half-life is 2 hours. Okay, and I want to know the total time it takes to go from my 20 grams and have it decay to 0.625. So I'm going to start cutting this in half because I know where to stop when I get to the 0.625. So 10 after one half-life, I'm going to have 10 or 20, I'm going to have 10 remain. Then I'm going to have 5 grams remain. And I'm going to have 2.5 grams remain. I'm going to kind of go up here because I didn't give myself enough room, 1.25 grams. And then when I divide that in half, I get to my 0.625 grams. Okay, so again, all I do is I have my starting and ending amount. I'm going to cut this in half until I get to my ending amount. And so what that tells me is that every arrow represents 2 hours. So 2 hours here, 2 hours here, 2 hours, all the way for every arrow. Because again, each arrow represents a half-life. So I can see then that when I go to find my total time, okay, I'm going to take my length of my half-life, 2 hours, and I'm going to multiply by how many arrows, not how many grams or like how many times I've divided it, in terms of, I always have students that will count the actual numbers, count the arrows. So I have 1, 2, 3, 4, 5 half-lives. So when I multiply those together, I'm going to get my total time, which is going to be 10 hours. Okay, so that's one way to do that. These questions, I'm really looking at your answer, but you need to come up with a very consistent method for how you're going to solve the questions for yourself. All right, so let's do another example. And in this case, we're looking at how much is going to remain. So I have 10,000 grams of francium-220. So this is my starting amount. Okay, I have francium-220, which I'm going to have to use table N for to get my half-life. And then it says how much will remain. So how much is at the end after 247.5 seconds. So this is my total time. Okay, so things that I know is I know I have 10,000 grams to start. Okay, I know my total time is 247.5 seconds. Okay, and I don't know what I have at the end after that total time. So this is where I'm going to have to use table N, and I'm going to be looking up francium-220, and I'm going to see with francium-220, it has a half-life of 27.4 seconds. So its half-life is 27.4 seconds. So I know that when this decays once, 27.4 seconds is going to pass. So I need to know, well, how many times does that occur in my 247.5 seconds? So this is the part that sometimes students have trouble with. I need to take my total time, 247.5 seconds, and I'm going to divide it by my half-life time, 27.4. Now, because it changes in the reference tables at various points, you might not get a whole number. Okay, so for me, I had 247.5 divided by my half-life time, and I get a number really close to 9. So we're going to go with that whole number of 9. So what that means is that this underwent 9 half-lives. So I'm going to be dividing my mass in half 9 times. Okay, so I'm going to start with my 10,000. I'm going to divide by 2, and I get 5,000, so that's 1. Divide by 2. So this is my second half-life. So then I have 2,500 divided by 2 again. So this is my third half-life. I get 1,250. I'm going to divide that in half again. 1,250 divided by, you guys can't see that, divided by 2. So this is my fourth half-life is 625. My fifth half-life is going to be 312.5. My sixth half-life is going to be 156.25. My seventh half-life is going to be 78.125. My eighth half-life will be 39.06. I'm just rounding that off at that point. And then this divided in half would be 19.53 grams. So that's how much would remain after this 247.5 seconds. Okay, and again, I did that by doing 247.5 divided by my half-life time for francium, which was 27.4, and getting 9, and then I had to divide this 10,000 9 times in half. Okay, usually it's not going to be that many half-lives, but in this case it was. Okay. All right, let's look at a different example. So that was how to figure out how much is at the end. In our third example, this is saying that I have a sample of cesium-137, so that's probably going to give us our half-life, the fact that it identified what isotope I have. It has an original mass of 52 grams, so I'm starting with that. It says, in this case, what fraction will remain after 150 years? So this is my total time. Now, in this case, it's talking about the fraction. So I made the mistake of just going ahead and writing in my grams, and I jumped ahead until before I read the fraction part. So I'm not going to use grams here because I'm going to deal with fractions. And one big thing with when you do fractions is we want to think of, we have one whole piece that we're starting with, and then we are going to cut that in half to see what fraction is going to remain here. So we know that this total time we're looking for is 150 years. I need to know how many times I'm going to cut that in half. So this is where table N comes in. So I'm going to look at cesium 137 has a half-life of 30.2 years. Okay, that's its half-life. So I need to know how many times does that occur in 150 years. So I'm going to take my total time and I'm going to divide it by my half-life time to see how many half-lives I have. So I'm going to do 150 divided by 30.2. And again, we're going to go with the whole number it's closest to. A lot of times it will actually give you the whole number. Okay, so we're going to go with that being 5 half-lives. So that means I'm going to cut this 1 in half 5 times. And again, I'm starting with the 1 because I want to know my fraction. So 1, when I cut that in half the first time, is going to be 1/2 that remains. When I go through a second half-life and I cut that in half, I'm going to have 1/4. Okay, when I cut that in half a third time, so a third half-life, be careful here, 1/4 would go into 1/8. Okay, my fourth half-life is 1/16. If I cut that 1/8 in half, and then my final fifth half-life, if I cut that 1/16 in half, I'll get 1/32. So this is my fraction that's going to remain. And just be careful, you could do this in your calculator as like a decimal form, but make sure you actually know what the fraction is that represents that decimal, because that's what you're going to be looking for there. Okay, so again, this was what fraction remains after total time. So I used table n to get my half-life. Okay, I figured out how many half-lives I had, and then I took my 1 whole piece, or 1/1, or 100%, and then I worked to divide it in half 5 times because I had 5 half-lives to get my 1/32 that would remain radioactive after that 150 years. Okay. All right, we have 2 more examples just to show you the other types of questions you could see. So in example number 4, we have the half-life of technetium-99 is 6 hours. So they're giving us the half-life time. It says if 10 micrograms were left after 24 hours, how much was originally present? So now we're looking at, this is how much is left at the end. Okay, this is my total time. And then we know that that's our half-life time. So in this case, I have 10 grams at the end, and I don't know how much I started with, but I do know that this took 24 hours. So in this case, I'm going to take my total time, because I need to know how many times did this decay to find my original amount. So I'm going to take my half-life time, my 24 hours, I'm going to divide it by, so my total time divided by my half-life time. Always use time units together. Don't start mixing in masses with this part. So my 24 hours total time divided by my half-life time, 6 hours, gives me 4. So that means I have 4 half-lives. And I want to go backwards here. So in this case, because I'm going to be going backwards in time, I'm going to end up multiplying by 2. Okay, so when you go back to find the one remaining, it's got to be getting larger because you're going backwards in time. So this would be my first half-life. So 10 times 2 would mean I had 20 grams present. Okay, now I'm going to go back a second half-life. I'm going to double that. That would have been 40 grams present. I'm going to go back a third half-life, which would have been 80 grams present. And if I go back my fourth half-life and I double this 80, I'm going to have 160 grams to start. So if you think about going forward, if I had 160 grams to start and 24 hours, I would have 4 half-lives, so I would cut that in half 4 times to get to that 10 that they gave me. In this case, we had to work backwards to get that. So that's one way to do this when you have to find the amount that's originally present. All right, our last example, this one is actually asking for the length of a half-life. So what is the half-life of a 500-gram sample if 135 grams remains after 20 hours? So this is my original amount. Okay, this is the amount that's left over, left at end. And then this is my total time. Okay, so in this one, I know I'm starting with 500. Okay, I know I'm ending with 100, and I'm going to guess this meant to say 125 here. 125. Okay, I know my total time here is 20 hours, and we want to know what's the half-life. Okay, so in this one, I know my starting and ending amounts, and anytime you know that starting and ending amount, you're going to start by dividing this in half. So I'm going to say, okay, well, my 500, if I go through one half-life, would be 250. Okay, if I go through a second half-life, I would get to that 125. Okay, so that means I had 2 half-lives in those 20 hours. So in order to find my length of a half-life, so you can't stop here. You can't say, oh, you had 2 half-lives. You have to find the length of each one. So in this case, I would take my 20 hours, I would divide that by my 2 half-lives, and that's going to tell me what the length of one half-life is, which is 10 hours. Okay, so that would tell me after 10 hours, I had 250 grams left. After another 10 hours, I had 125 grams left. So that gave me that. You do have equations that you use in math that you can do this with in terms of just helping you do some of these calculations, especially with fraction remaining that you might be interested in. So I'll show you those more in class in case you need them. But besides that, you are all set, and it's just going to be some practice and doing lots of examples so that you feel comfortable.